All right. All right. So hopefully you guys can hear me. So this is going to be a super short video. This is for week 5 of material science, and this is the first part mechanics. And it's not going to be too bad. Well, I don't think. I hope it's not. And as always, any questions, come reach out to me and Vincent. We're always available to help. So I only have 3 examples, and they're not too long. And hopefully the problem set doesn't take you too long either. This is more for the actual mechanics part. So let's just look at the first question. So this is for the calculation of, or the elongation for elastic elongation commutation. So a piece of copper originally 305 millimeters. We don't care about 12 inches. We don't use an imperial system here in science. Long is pulled in tension with a stress of 276 megapascals. Okay, if the deformation is entirely elastic, which means, remember, elastic deformation means that if we have a shape, oh, which means if we have a shape, hard to get this out over here. Oh, we can't draw. Okay, anyways, what was it? So if the deformation is entirely elastic, what will be the resultant elongation? Okay, so if I can find get something right here. There. Whoops. I'm still trying to work out the kinks of these iPads and such. Not the best, obviously. So, okay. So we're given that this entire thing is elastic deformation. So what that essentially means is that if we have a piece of copper like this, and then we cause this to deform, so say I made it longer like this, what will happen by nature of it being an elastic deformation is that it will actually return to its original shape like this. So this is what we're working with. And remember, going back to the slide, within the elastic region, so say this is my stress strain graph. Stress strain. Sorry, I just completely, it's late at night right now. I'm doing this at like 10-ish, no, 9 o'clock at night, and I just came back from school, so my brain's a little fried. So remember, on a stress strain curve, this would be the stress, and this would be the strain. So strain or stress refers to the amount of force in newtons. Well, newtons over area squared. Newtons over area, I should say, to be more exact. And then strain is essentially the elongation. So how much does this thing actually change in shape, which is measured by the length. All right, so remember, in the elastic region, this is the elastic region where it's all completely linear. So this is the region that we're working in. And remember, in this region, because it's linear, we can use Hooke's law. So the stress is equivalent to the elastic modulus, which is a constant, was it multiplied by the strain, or the strain, which is represented with this epsilon. So it's not an E, it's an epsilon. Yeah. And then we should also note that when it comes to this strain, we should also note, oh my gosh, these iPads, I'm not going to get used to them anytime soon, am I? We should note that epsilon is equivalent to, remember this is strain, the change in length divided by the original length. So if I were to write that out, change in length and original length. So really what we can do is that we can actually plug this epsilon into this equation over here, Hooke's law. So then the resulting equation we get from there is the stress is equivalent to this rewritten version of the strain multiplied by the elastic modulus. And then what we can actually do is that we can actually do some algebra in order to figure out what is this change in length. Because if you go back to the question, if we were to go back over here, is asking us if the deformation is entirely elastic, what will be the resultant elongation? So elongation refers to the change in length, which is what this delta L represents. So this represents elongation. Okay, so then let's just do some algebra to figure out what is our elongation, or what will be the formula that we use to get that. So what I'm going to do is that I'm going to make this a little clearer. Divide by the elastic modulus. So now I'm left with delta L over the initial length over the stress over the elastic modulus. And what I'll do now is that I will multiply by the original length on both sides. So I cancel out the original lengths on that side, and now this is my resulting equation. So the elongation, delta L, is equivalent to the stress multiplied by the original length divided by the elastic modulus. Perfect. So this is what we want. Okay. So now that we have this, let us go on with our day and actually solve this thing. So let's figure out the information that we have. So let's go over here. So let's see. So it's pulled in tension with a stress of 267 megapascals. So that is the stress that's explicitly given to us. So the stress is 276 megapascals. And our original length is 305 millimeters. Okay. So original length is equivalent to 305 millimeters. And you might have noticed that the question did not give you what this elastic moduli is. And you're right. That's because I need to give you that. So I'll give you that right now. And just to make your life extra easy, I will give it to you in megapascals. And I'll tell you why that's going to make your life extra easy. It's going to make your life and my life extra easy. So the elastic moduli for copper is going to be 110 times 10 to the third megapascals. Pretty conveniently, right? And I'll show you why by actually using these numbers. So if I were to plug in these values, well, we have 276 megapascals multiplied by 305 millimeters divided by 110 times 10 to the third megapascals. And you notice, look at the units, and I'll do this in green. You'll notice that the megapascals is both in the numerator and the denominator. So what that basically means is that we can cross out these megapascals. And essentially what we have is a ratio. And then from there, we can just figure out, and from here, the only units left is millimeters, which is the units for length. And that's the reason why megapascals is so convenient in this case. However, if I were to give you this value in, say, I don't know, something gigapascals, then what you will have to do is that you'll either have to convert this gigapascals into megapascals for the elastic moduli, or what you can alternatively do is that you take this stress, which is in megapascals, and then convert that into gigapascals. So that's the way you do it. And just a quick reminder on how to do that. You have to use the fact that giga and mega refer to some power of 10. So for example, if I want to, I'll do this in red. Let's just say I wanted to convert the stress of 276 megapascals into gigapascals. I don't know how much that is. Well, what I'll do here is that 206 or 276 megapascals will, in 1 megapascals, there are 10 to the 6 pascals. Because remember, this M, or not remember, I didn't tell you guys this, but customarily, M represents mega, which represents a power of 10 to the 6. So then what'll happen is that these megapascals cancel out, and I'm left with pascals. However, I want my answer in gigapascals. So what I'll do here is that, 1 gigapascals is equivalent to, I believe giga is 10. Let me double check what giga is. Is giga 10 to the 9? Yes, okay. So giga is 10 to the 9 pascals. So that means 1 gigapascal has 10 to the 9 pascals. So essentially what I'm doing here is dimensional analysis. So then if I were to actually multiply everything out, let me get my calculator. So getting my calculator over here, I do 276 times 10 to the 6 divided by 10 to the 9th. And I get 0.276 gigapascals. So essentially what I did here is just dimensional analysis. However, in this case, because the elastic moduli was given in megapascals and the stress was given in megapascals, I don't have to worry about dimensional analysis here. But I just show you that case with dimensional analysis in case you guys do have to do that. So anyways, going on with the rest of the problem. So we have this value over here. And if we were to actually plug that into our calculator, we get a value of 0.77 millimeters. And this is the value that represents the delta L, which is the change in length, which is synonymous to elongation. So therefore, that is our final answer. And remember, the megapascals are in the numerator and denominator, which means they cancel out, no units except the millimeters. The millimeters is the only unit that is left. So that's the first question. Moving on to the second question. I'll do this in yellow. So let's read the second question. Oh, okay. So I didn't put the second question on there, but the second question is essentially asking you, what is the elastic modulus for this brass specimen? And I gave you the stress and strain graph. So the way you do this one is that you have to remember that when it comes to the elastic region, which is where you will find the elastic moduli, if we look at Hooke's law, which represents the elastic moduli or the elastic region, we see that it's a linear graph. Linear graph. Well, so then that means this represents the y value, this represents the x value, and this elastic moduli represents m, or the slope. So that means if we're looking at an elastic region and we want to find the elastic moduli, we need to find the slope of the part that's actually linear. So let me pick 2 points that are convenient for me to find the slope. So the easiest point here will obviously be a strain of 0 and a stress of 0 megapascals. So that's going to be my point 1. So point 1 will be 0, 0 megapascals. Okay, that's point 1. What about point 2? So point 2, let's look on the graph for something convenient. Let's see here. So let me label this over here. So this would be 0, 0. Where can I look next? One thing I can do is that I can look at this. So this would be 150. It's not very clear. Let me do this in black. So this would be 150 over here. And I can draw dashed lines to figure out where that is. So then if I were to draw that downwards, okay. So then it's roughly around there. So this will be another point that we can use. So we know that it's some elongation and 150 megapascals. Well, let's figure out what this strain is. So, oh no, that's the wrong direction. Strain. What? That's not right. Oh, sorry. Yeah, it's way too late at night for this. So let's figure out what the strain 2 is. Okay. So we can quickly figure that out by counting the x-axis. So if you follow over here, it's 1, 2, 3, 4, 5. Okay. So then 5 ticks in order to get 0.005. So that means 1 tick represents 0.001 for strain. So then that means this tick over here represents a strain of, let's just say 0.002, because it looks to be around there. Okay, so then that means strain 2 is 0.002. So now I have my 2 points. So point 1 will be 0, 0, convenient, and point 2 will be 0.002, 150 megapascals. All right, so then let's actually calculate the slope in order to figure out our elastic moduli. Megapascals, and then for the slope elastic moduli, that's going to be change in strain, or sorry, stress. Stress goes in the numerator, divided by the change in strain. So then that's going to be stress 2 minus stress 1, strain 2 minus strain 1. So then that's going to be 150 megapascals minus 0, and that's going to be 0.002 divided by 0. And remember, elongation is technically a unitless value. So then if I were to plug this into my calculator, I should be getting gigapascals. Hold on, I'm just looking at my answer key and I think I messed up. Whoops. Oh, sorry. 150, so then plug into my calculator. I get roughly around and of course, like these are all technically approximations, like nothing will be perfect, but it will be close enough. So I'll get roughly around 75000 megapascals. So this will be my answer. And that's it. That's that for calculating the elastic moduli. So moving on to the last question, I'll do this in green. What does the last question say? So, oh, okay. So this is flexural strength. So a 3-point bending test is performed on a spinel specimen having a rectangular cross-section of height d equals 3.8 millimeters and a width of b equals 9 millimeters. The distance between the support points is 25 millimeters. Compute the flexural strength. The load at factor is 350 newtons. All right, so let's figure out what this thing looks like. So the way this thing looks like is that 3 points. So it's going to assume a more rectangular shape. So then it'll look something like this. Obviously not as thick, but roughly around this. And then we have the force over here. So then 350 newtons. And this will be our length. Our length, this will be our B value, and this will be our D value. Okay. So the first thing we should really do is get everything into the same units. Yeah, so get everything into the same units. So we were given, actually everything's in the same units already. But actually, yeah. So what I'll do is that I want to convert all my values in millimeters. So for example, for L, which is the point in between the two, what do they call them again? Yeah, so the distance between the two support points. So these would be the support points. If I were to label them in blue, support points. And this one over here is going to be in, what was it? 25 millimeters. However, I want to get this in meters. And the reason why I want to get this in meters is because the flexural strength is going to be, so flexural strength is represented with sigma Fs. The units for that are in megapascals. Megapascals, which is equivalent to meganewtons. Meganewtons per meter squared. Yeah, so meganewtons per meter squared. And notice how it says meter squared and not millimeter squared. So then just because of that reason, I want to convert all my millimeters into meters so then I can account for that and actually get pascals and not some other weird unit. So in order to convert this into meters, I'm going to use some dimensional analysis. So 1 millimeter has 10 to the negative third meters. Okay, so millimeters cancel out, left with meters. I get 0.025 meters. Great. For my B value, I get 9 millimeters, as stated in the problem. So then using the same conversion factor I did on top, 1 millimeter has 10 to the negative third meters. Meters cancel out, I get 0.009 meters. Same process for D, 3.8 millimeters, exact same conversion factor, and I get 0.0038 meters. Perfect. So now I can start plugging things in. But what equation do I use? Well, I can use flexural strength. So Fs represents flexural strength is equivalent to 3/2 the load force multiplied by the L multiplied by BD squared. So then I'm just going to plug in my values. So 3/2, was it the load, the force at fracture was 350 newtons. So 350, that's not very clear. 350 newtons multiplied by L, which is going to be 0.025 meters divided by 0.009 meters divided by 0.0038 meters squared. And I will get my desired units because if you look over here, was it megapascals? Actually, wait, sorry. Yeah, because megapascals is going to be equivalent to meganewtons over m squared. So I have newtons in the numerator, which I'll mark up in red. So newtons is in the numerator. And if you look in the bottom, I have 1 unit for meters here, and then 1 over here for the denominator. However, because of this square and this meter over here, this will actually become meters squared. So then this denominator, if I'll write over here, so I have meters in the numerator, I actually have meters cubed in the denominator, but I have meters on both sides, or both the numerator and the denominator. So then this meters cancel out. This 3 becomes a 2. So now I'm left with 1 over meters squared. And remember, because of this numerator over here, I really have newtons meters squared, which is what I want. Now you might be saying it's not the same as meganewtons. Well, that's just another conversion factor, a scalar of multiplying that newtons over meters squared by some factor of 10. So really it should work for us. So let's actually plug in and see what we get here. Okay. Oh, whoops. I forgot. I did not plug that into my calculator correctly. Mhm. And then divide. Huh. Hold on. Did I mess up a calculation somewhere here? Might have messed up a calculation because I'm not getting something correct here. One moment, what I think here. Hmm. So that's going to be 0.0038. That's going to be raised to the second power, multiplied by 0.009. And then for the numerator, 350 newtons to multiply by 0.025. So divide those and then multiply 3 over 2. Okay, yeah, okay. Sorry, I was not plugging things in my calculator correctly, which is why I was not getting the right answer, but I just did now. So you see in the calculator, I get 1.009922613. Let's do pascals. Actually, no, I shouldn't do pascals. I mean, I can do, but since I mentioned newtons over meter squared so many times, I might as well do that. Remember, pascals is equivalent to newtons over meter squared. And you might think to yourself, wow, that's a very large number. Not very practical now, isn't it? And you're right, it's not very practical because I would not want to work with that number if I were you. So what I'll actually do is that I will do was it 100992613 newtons over meter squared, and I'll actually convert this into meganewtons. So 1 meganewton has 10 to the 6 newtons. So the newtons will cancel out. And once I actually divide, I get 100 point, well, I'll just round it off to the 3 sig figs. So 101 mega newtons over meter squared, which is equivalent to 101 megapascals. So that will be my flexural strength. And that's why I said over here, even though I got, was it, newtons over meter squared, it's not that big of a problem because I know I did say I wanted this in megapascals, but if you look at the megapascals, well, mega is just a suffix that represents 10 to the 6. So it's not that big of a problem if I get newtons over meter squared because I can then just easily use a conversion factor in order to get megapascals. So hopefully I didn't lose you guys. And as always, if there's anything I should clarify, please let me know and contact me or Vincent. And see you later.